Hi guys, Miss Onay here. Unfortunately, I can't be with you in class today, so I figured I would make you a little bit of a video for review. So just like you guys requested, I'm going to go through a couple questions from each unit. You guys will watch it. You guys should probably do this and follow along with me. I'm going to be looking at your big ideas packet, and I'm going to also be doing some other things that I've found to be really important for each unit. So take out that big ideas packet, and we will be working from questions in there from each unit, and then you guys can work on them, chat with your partners, and then we will talk about them at the review session on Sunday. Just a reminder, Sunday review session, it's going to be in room 2104, and we start at 3:30. So Sunday at 3:30 p.m. in room 2104. That's right above the Patriot. Okay, so don't forget, make sure you come with your packets, final exam review packet. I will have that for you. Okay, so we are going to actually start today with Unit 1 and Unit 2. Unit 1 and Unit 2 both cover the idea of motion, okay? Both of these talk about motion. This is where we introduce our D versus T graphs, our V versus T graphs. We talk a little bit about F equals ma. We are looking at mass versus weight, Newton's first law, motion diagrams. This is where you get your first idea of FBDs. And so in order to start this, I just want to look at D versus T and V versus T graphs, okay? That's what I want to look at for Unit 1 and Unit 2. So I'm going to just make a bunch of D versus T and V versus T graphs for different types of motion, okay? So we went over this in one of the review sessions that I already had, so if you were there, then this will be a nice little refresher. So in a D versus T graph, the slope will be distance, rise, over time, which is run. If you look at the units, distance is in meters, and then we have time, which is in seconds. Okay? Our slope is meters per second. What variable do we know has the units of meters per second? Velocity. So the slope of a D versus T graph is just velocity. Now, let's look at a V versus T graph. Okay, we're doing rise over run again, velocity over time. If I look at the units, velocity is meters per second. We just said that. Over time, which is seconds. So I'm looking at meters per second, which is also known as meters per second squared, which is dun, 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 acceleration. So the slope of a V versus T graph is acceleration. These are really important pieces to know because this will make completing the graph so much easier, okay? So I'm going to take a look at the first D versus T and V versus T graph. A D versus T graph. Let's say the situation that I'm doing a D versus T is to increase speed. If I'm increasing my speed, I am increasing my velocity, right? That's what my slope is going to be. So to be increasing my velocity, I need to increase my slope, okay? I'm telling you that slope of a D versus T graph is velocity. So to increase speed, I need to be increasing velocity, meaning I need to making that slope steeper and steeper. If you look here, the slope here is a lot more level than the slope up here. So I've made it steeper, which means I have increased speed. If I wanted to follow up with a nice V versus T graph, all I'm doing is increasing speed. If I'm increasing speed, that means there is some sort of acceleration present. And I can just draw a nice that shouldn't be squiggly, you guys. A nice straight V versus T increase, right? I'm increasing my speed. In this case, you can even just reason it. As I'm increasing my velocity, time also is being increased. So over time, I am increasing speed. Okay? Let's do another one. So now I want to do a D versus T graph for when I'm going at a constant speed, and then I increase my speed. So we know the second half of my graph will look something like the first one that we just did. At a constant speed, my velocity, which is my slope in a D versus T graph, is unchanging. I'm not speeding up or slowing down. All I'm doing is going at a nice constant speed, right? Then I'm going to change my motion. So I'm just going to put a little line here just for me to recognize I'm going to change my motion here. This is also a really good idea to do on the test. So now, after being at constant speed, I need to increase my speed, which means I need to increase my slope, make it steeper. Okay, here I've got a more level slope, and as I go up to the top, I'm getting steeper and steeper. That is a D versus T for constant, going to increasing speed. Now, let's translate that to a V versus T graph. At a constant speed, do I have acceleration? The answer is no. But I am going at some sort of speed. So I can't just put my line at 0. I am traveling at some velocity. It's just constant, meaning there is no change in velocity, which means there is no acceleration. So I'm just going to put a nice straight line here. There's no acceleration happening, but it is at some velocity, right? I'm not here at 0. I could be at, let's say, like 2, okay? So there is some sort of velocity first at a constant. Then I speed up. Nice and easy here. I'm just going to speed up. This is also a nice straight line. So, again, important to know, slope in a D versus T is velocity, slope in a V versus T, acceleration. Awesome. So let's move this down and look at the next set of graphs. All right, the next graph that I have for you, D versus T, and I'm looking at decreasing speed. Then, right after that, increase speed. Sorry, my handwriting looks messy here. So, decrease speed, and then go to increasing speed. So this one is going to be a tricky one, okay? Decreasing speed means I am decreasing my velocity. So my slope of D versus T is velocity. So to decrease speed, I need to show a decrease in slope. So before we showed our slope getting steeper, here I'm going to show my slope becoming less steep or more level. Okay? That's my decreasing speed. And now, to increase speed, I have two options here. In the graph, most likely what we'll see, to increase speed, now I have to increase my slope. So I'll just kind of go from here and make this nice little S shape kind of thing. First, I have a slope that is becoming more level, then I have a slope that is becoming more steep. So I'm decreasing speed, and then I'm increasing. Or you could also have your increasing speed come back this way. I would accept both ways. Then in a V versus T, we've done this one multiple times in class. First, I'm decreasing my speed. There is acceleration. If I'm decreasing my speed, there's acceleration. And then I'm going to increase my speed. Okay? Very simple. As you've noticed by now, you guys, V versus T graphs like this and the ones above will always, or most likely, going to be very linear. We won't be changing the slope to be steeper or to start leveling off. It's very linear. Next one we're going to do is we're going to do d versus t for constant speed, and then you're going to slow it down. So a decrease in speed. Constant speed, like I said before, velocity is not changing, so I have a nice constant rise over run here. Straight line. Then decrease speed, I want to decrease my slope, so I want to level my slope off. I want to go from steeper to not as steep, like that. Then I want to make the corresponding v versus t. Corresponding v versus t, constant speed, there is no acceleration, but I am going at some speed. There is not zero velocity, so let's say I've got a velocity of like 4 or something. This is constant, it's not changing. And then I need to decrease my speed. Decrease my speed. Awesome. Last one that we're going to do today, we're going to do d versus t, and we're going to say just decreasing speed. Nothing fancy. Decreasing speed, d versus t, and a v versus t. So my d versus t is going to be decreasing speed, which means my slope, my velocity needs to decrease. So I'm going to level off my slope just like this. Decreasing speed for v versus t, a nice straight line. My little stylus here does not want to make a straight line. Just like that. Okay? So hopefully you guys can write this one down and then just be able to reference it and go through and just really understand your d versus t and v versus t graphs. I know it can be tricky, but if you think of it in terms of slope, you will be in good shape. Okay. Awesome. So that was not anywhere in your final exam review packet, big ideas packet, but these next portions are going to be. So the next section we're going to be looking at is Unit 3, and we are going to be looking at your big ideas page, number 3 actually. So Unit 3, page 3 in the Furby. Page 3 in your final exam review, big ideas. Alright, so turn to page 3, you guys. Unit 3, as you can see, it's all about forces, push and pull. We've got those FBDs. We're looking at our F-net equations, and we're looking at Newton's first law on object in motion and at rest will stay in motion or at rest unless acted upon by an outside force. So I'm going to be doing number 2, which is in the solving Newton's law problems. You guys will be doing that with me, okay? This is one that I think really encompasses a lot of the Unit 3 big ideas. So we're going to be doing question number 2. It first says that you have a 160 kilogram wagon is pulled by a rope horizontally across a rough surface with a force of 70 newtons. The force of friction is 35 newtons. Draw an FBD. So here I've got my wagon. It's being pulled by a rope horizontally. If I know it's being pulled by a rope horizontally, that's going to give me a force of tension. They also tell me that there's going to be a force of friction, so I've got an F of F. Now I'm not quite done yet because I know my wagon is not flying in the air and it's not falling through the ground, so I'm going to have F of G, force of gravity, and then of course normal force, F of N. These are my 4 forces in my FBD. So that is part A. B says, what is the acceleration of the wagon? So in this case, we need to look at what the acceleration is. So what equation do we know to find acceleration using FBDs and F-net? That's going to be F-net is equal to M times A. So if I were to draw F-net here, do I need to consider all 4 forces? Yes. However, you should know that because my wagon is neither falling through the ground or being flown up in the sky, these two, F of N and F of G, are equal in magnitude and opposite in direction, these guys will cancel out. So F net in the y direction is actually 0, right? F of n and f of g have to be equal and opposite. So when I talk about f net, I'm really only looking at f net now in my horizontal direction, okay? So f net is equal to m of a. What's f net in the horizontal direction? That's going to be ft plus f of f is equal to m times a. So we know that ft is going into the right direction, f of f is going to the left. So if we were to give these their directions, f of t will be positive, and then we'll have a negative f of f is equal to the mass. They tell me the mass is 160, and I'm solving for acceleration. So do I know f of t? Yes. They tell me the force of tension is 70 newtons, and they tell me that the force of friction is a negative 35. Well, it says 35, but I know my force of friction due to my FBD is negative, is equal to 160 A. 70 minus 35, do that in your calculator. You guys should get 75 minus 35 is, or 70 minus 35 is 35, which is equal to 160A. So to solve for A, I'm just going to divide this guy over. A will be equal to 35 divided by 160, which is 0.22 meters per second squared. So 0.22 meters per second squared. Now, before you circle your answer, acceleration is a vector quantity, meaning it has direction, and we are saying acceleration is in the positive direction. Good. We're not quite done yet. We still have C. It says, what's the normal force? So now they're asking me to solve for the normal force. So you guys might be thinking, how do I figure this out? Well, we need to think, we're looking at f of net in the y direction. If you look at what we talked about earlier, we just said f of net in the y direction is actually equal to 0. So I'm saying if I'm just looking at f net in the y direction, if I had to add these two together, it would be f of n plus a negative f of g. I know f net y is equal to 0. So I can make the relationship. I can add f of g over and get f of g has to be equal to f of n. This is definitely true because we said earlier that these two guys will cancel out because they're equal and opposite in magnitude and direction. So f of g is equal to fn. I can actually solve for f of g, which means I'll get f of n because they're equal. F of g is m times ag. So I'm looking at force of gravity is equal to mass 160 times acceleration, which is a negative 9.8. My force of gravity, F of g, is equal to a negative 1,568 newtons. This makes sense that this is negative because we see that in our FBD, our f of g is pointing in the downward direction. So what is f of n? Equal and opposite. That means f of n has to be a positive 1,568 newtons. Awesome. So that is the question that I wanted to work on with you guys from Unit 3. We are going to next go to Unit 4, which we talked a little bit about yesterday. So turn to page 4, and we're going to be looking at the bottom of the page. All right. So Unit 4, we're going to take a look at that. We're at the bottom of the page. I'm looking at the part where it says proportional reasoning with AC and calculations with AC. So Unit 4. So we are looking, yesterday we looked at the Newton's fancy gravitation equation. You guys worked through that. Now we're looking at AC. So we have got AC is equal to V squared over R. So proportional reasoning, the best way to do it is anything that we're not discussing or that's constant, plug in a 1, and anything else that it tells you to do, plug in that number, and then that will be how much times the original the answer will be. So it'll make more sense as we go. So the first one says, what happens to AC if V doubles? If V doubles, what happens to AC? So I'm looking at if I change V, what will happen to AC? They don't mention R, which means I can keep that at a constant, so I'll just plug in the number 1. So AC is equal to V, they're telling me it's doubling, 2, but V is squared, and then R is staying constant. I'm just going to put it as a 1. 2 squared is 4 over 1, which is equal to 4. AC is equal to 4, which means acceleration due to gravity is 4 times as much. So you could say 4 AC. What happens to AC if R triples? So I'm no longer concerned about V, so I'm going to put a nice little 1 there. And then if R triples, 1 squared is 1 over 3, AC would be equal to 1/3. So that would be 1/3 of the original acceleration, centripetal acceleration. Last but not least, AC says, what happens to AC if R is 1/2 as much? Not concerned about V. Put 1/2 down here. 1 squared is 1 over 1/2. 1 divided by 1/2 is equal to 2 AC. Okay? So proportional reasoning, we've been doing this all year. If you are looking for answers still, please write it in our Google Doc, ask me questions, let me know, okay? All right, we're going to do the calculations with AC right next to it. All right, calculations with AC. It says, what is the centripetal of acceleration? So I'm looking to solve for A of C. What is the centripetal acceleration of a space shuttle traveling at a velocity of 7,800 meters per second? It takes the shuttle 2.1 hours to orbit. It takes the shuttle a time of 2.1 hours to orbit the planet once. It says, hint, convert the time to seconds, then find distance. So the first thing I'm going to do is convert my time to seconds. So 2.1 hours. There is, in 1 hour, there is 60 minutes. And in 1 minute, there are 60 seconds. So I'm going to just do this nice little multiplication problem. 2.1 times 60 is equal to 7,560 seconds, right? That's what the unit I'm left with. So I've converted my time into seconds. Then it says then find distance. So distance, if you look in your equations, is 2 pi r. I don't know the radius, so I can't really just plug in to solve for distance. And I know I'm looking for AC, and AC is equal to V squared over R. So I definitely need to find R because I need R to solve for AC. So what I can do is I do know the velocity and I do know the time. I'm looking for distance, so I could say V is equal to d over t, and plug in, instead of putting distance, because I don't know that, I'll put 2 pi r. 2 pi r over t. So I've got my equation of v is equal to 2 pi r over t. Can plug those numbers in. I've got v is 7,800 meters per second, 2 pi r over time, which is 7,560 seconds. If I multiply these across and then divide by 2 pi, you get an answer of r is equal to a huge, huge number. 9,385,049 meters. So I've solved for r, which means I can now solve my acceleration, my centripetal acceleration. So all I do is plug in. I've got a of c is equal to v squared over r. V, I found v to be equal to 7,800 based on my givens, squared over r. I just solved 9,385,049 meters. If you solve that, you will get acceleration equal to 6.48. What's the units? Meters per second squared. Okay. Acceleration is also a vector. Awesome. So that wraps up our section of Unit 4. The last two units, Unit 5 and 6, you guys, this will go really fast because we just took our target retake on it and we talked a lot about it earlier. All right. So we've got Unit 5 in your final exam review packet. This is page 5. The question that we're going to look at is all the way at the bottom where it says during the Cotton Bowl. So I'm looking at during the Cotton Bowl, MSU's Tony Lippett, which is, he has a mass of 85 kilograms, was running at a speed of 6 meters per second when he hit Baylor's Chris Callahan, second mass over here, 80 kilograms, who was running at him 5 meters per second. So if I were to draw these two guys, I've got my 85 and my 80 kilogram. They are running at each other. So one of them is going to have a positive velocity, one will have a negative. So let's just say 85 kilograms, he's running to the right, he has the positive 6 meters per second, and then 80 kilograms running to the left, that's a negative. Okay? So it says, what was the total momentum after the collision? We know that based on conservation of momentum, that momentum before has to be equal to momentum after. So all I have to do is solve for 1/2 of the equation, which is momentum before or after in a bouncing would be m1v1 plus m2v2. So whatever this is equal to is what also is equal to what happened before, because momentum is conserved. So m1 is 85, velocity plus 6 plus 80, negative 5. This gives me a total of positive 110. The units are kilogram meters per second because we know momentum is equal to mass times velocity, which is kilograms times meters per second. So 110 kilogram meters per second is the momentum after the collision, just like it's the momentum before the collision. The next part, it says if Lippitt comes to a stop, which is the 85 kilogram guy, if he comes to a stop, what will Callahan bounce back at? So now I know I'm looking at a full bouncing elastic equation, and I am just given the new velocity of one of my players, and so I'm just going to fill in the before as we did earlier. And then I'm going to multiply M1. It says we're looking at if Lippitt comes to stop. Lippitt is our 85 kilogram. If he comes to a stop, his velocity is going to be 0. And then we know this guy has a mass of 80, and we're solving for V there. So we know from above this is equal to a positive 110. And then this will be equal to 0, so I'm just solving 80V. Divide 80 by 110. You're going to get a velocity, which is a vector, positive 1.38 units of meters per second. Awesome, guys. So, last but not least, turn to the last page in your packet. I'm going to be super short in this because you guys rocked all of Unit 6. So we're going to look at just the last question with Unit 6. I just want to briefly talk about the drawing that you guys see on Unit 6 with the roller coaster. They tell you the different types of heights here. The first one is 30, second one is 10, and the third one is 25. Alright, here's my roller coaster. And then we've got, this is A, this is B, and this is C. So I just want to really quickly go over, you guys know how to do these graphs, you guys are good to go. Remember, total energy needs to be the same. Thermal energy is only created once their friction is occurring. And this question does say assume friction occurs with 5,000 joules between A and B, and then another 5,000 between B and C. So they're telling you there is going to be some friction that occurs from A to B here. That's going to be a lot of it. There's going to be, well, not a lot of it, it's 5,000 joules. And the same amount is created between B and C, another 5,000 joules of thermal energy. Okay? So a lot of people end up having the question, well, how do I know if kinetic energy or potential energy is higher at each point? So the first thing that we can say is just what we know already. So up here at point A, we know there's not even an argument if there's any potential versus kinetic, right? We know that we're not moving yet, so this is potential maximum. There's no kinetic. So that's not really an argument. What comes important is here at B versus here at C. So at B here, I just want to say that I'm coming from point A where I'm stopped, and then I go down this steep hill. I gain some friction, but at point B, that's where I really should have the most amount of kinetic energy. I should have, out of those three, that's where my kinetic energy is going to be largest. I'm on my way down to the ground. I'm closest to the ground there, which is where I would have the maximum kinetic energy. I'm going to have some thermal, and they tell you how much here, and what's ever left over to get to the equal total energy will be potential, and it's going to be pretty small. Then here at C, you will notice that it's the same amount of thermal here. Same amount of thermal, still 5,000. But our potential and our kinetic end up switching because now I'm at 25 meters. The original height where I'm at a max of UG is 30 meters. So you can say that you know for sure that UG will be larger, right? That's going to be your larger source of energy. You're going to have some thermal, which is going to be the same between B and C, both 5,000. And then you're going to have kinetic, which will be smaller than potential. So just really look at the pieces that the question is giving to you, right? 25 meters is a lot closer to 30 meters than 10 is. So you can say that UG here is going to be really high or really close to my UG max here at 30. All right, awesome. Well, thank you so much, you guys, for listening. What I would like for you to do now is to move on and please write 2 questions in our Google Doc that you would like me to address during Sunday's review session or that you would like me to answer before finals happen next week. For the remainder of the time, you guys will be working on your final exam review packet and hopefully being able to get the opportunity to look at some of the keys. Thanks for listening, and I will see you guys on Sunday. The rest of you, see you Monday.